In this video, I wanted to discuss diagonalization of a square matrix. Okay, this isn't always possible, but sometimes it is. All right, definition here. Okay, A is a real n by n matrix, or it could be actually complex matrix, but we're going to focus on real mostly. Okay, then A is said to be diagonalizable if there exists an invertible matrix P such that P inverse times A times P is D, where D is a diagonal matrix. Again, you remember what a diagonal matrix was? A diagonal matrix is a square matrix, in this case also n by n, where all the entries off the main diagonal are 0. Okay, so I've sort of indicated that here. So all the entries off the main diagonal are 0. Okay, what goes on the main diagonal is anybody's guess. Okay, all right. Now you should recognize this form P inverse A P. Okay, with reference to what? Similarity, right? So what's another way to think about diagonalizable matrices is what? Matrix is diagonalizable if and only it is what? Similar to some diagonal matrix. Okay, in this case D is what we were calling it. But that's the idea of being diagonalizable. Okay, all right, let's get a theorem on diagonalizability here, and we'll go through the proof here. Okay, some emphases here. An n by n matrix A is diagonalizable if and only if. So this is going to work both directions, as we'll see in our proof here. If and only if there exists an invertible matrix P given by P equals x1, x2, out to xn. These are what? Column vectors. So these are the n columns of P, because P is also an n by n matrix. Okay, but P's got to be given this way, and it has to be invertible, right? Otherwise we couldn't write this up here. Okay, it has to be invertible. And here's the punchline though. The x1, x2 to the xn, the columns of the matrix are actually eigenvectors of A. Okay? Now here's a little bit more here that we will also see. If A is diagonalizable, then the corresponding eigenvalues of A are actually the diagonal entries of D. Okay? So the entries down the main diagonal will be corresponding eigenvalues of those various eigenvectors up here. Okay? And we shall see that. All right, let's go ahead and get a proof here. Okay? We're going to start like this. Suppose this P exists here, and it has an inverse. Okay? Now I've written y1, y2, y bar n, but transposes here. So these are actually what? These are row vectors. Okay? These are written as row vectors here. That's why you see those transposes there. Okay? And again, P is written this way with the x bars here. Okay? Well, you see that. Okay? Now, the product of these two is supposed to be what? The n by n multiplicative identity. So I've got P inverse times P is I sub n. Okay? Now, if I was to actually multiply these two matrices together, now you see what would happen here. To get the first column of the product, I would have what? The first row times the first column, the second row times the first column over here in P, and so forth, all the way down. Okay, so I've written that there. Y sub 1 transpose x bar, x sub 1 bar. Y sub 2 bar transpose x sub 1 bar, and so on and so forth. Y sub n bar transpose times x sub 1 bar. Okay, and then so on for each column here. Okay? Okay. In the second column, I'm multiplying by x sub 2 bar and so forth. Down in the last column here, I've got product on the right being x sub n bar. Okay? Alrighty? Alright. So this is just exactly what you get if you were going to multiply these together. Now, what was this supposed to be, though? This was supposed to be the multiplicative identity. That's a diagonal matrix, right? That has ones down the main diagonal and zeros off the main diagonal. So you could see here, if these two, now I've written this with subscript notation, y sub I bar transpose times x sub j bar, okay, that would be one of these entries right here. Okay, that would be some entry, right? All right. You can see that this, because the product is supposed to be the multiplicative identity, that this is going to be what? This product is going to be 1 if I and j are the same. Those are the entries down the main diagonal, right? But if I and j differ at all, if they're different at all, then I should get what? Zeros off the main diagonal, so I've got this product being 0 if I and j are different. Okay? Now, keep that in mind then. If I go back and go P inverse AP, then what I've really got here, here's my P inverse, right? Okay, there's my P inverse. And then AP, if I go A times the matrix A times P here, you see what I'm going to do is just go what? A times the first column, A times the second column, so on and so forth, down to what? A times the nth column. And this is going to be gives me the column of the product, A times P. Okay? That's what you would get here. But wait a minute. Remember that these x sub i's are what? These x sub i's are actually eigenvectors, we're assuming. Okay? So we're moving that direction. Okay, so this becomes what? I'm using lambda again as my, your book does this too, actually. But I'm using lambdas again as my eigenvalues. Okay? So A times x sub 1 bar should be lambda 1 x sub 1, right? A times x sub 2 bar should be lambda 2 x sub 2 bar, and so on and so forth, all the way down to the end, okay? Which is going to be nice because these are just scalars here. And now when I take this column and multiply it here on the rows down this matrix, notice because that's just a scalar, I'm going to be lambda 1. I'm going to be multiplying lambda 1 times just what I got here. But what did I get right there, that first column? That first column would be 1 with zeros all the way down, right? Why? Because the product is I sub n, right? It's the n by n multiplicative identity. So if I multiply that by lambda 1, then I get lambda 1 instead of 1 in that place, but zeros all the way down here. Okay? Likewise, when I go lambda 2 times x sub 2 bar, and it multiplies on this, I'm going to get just lambda 2 times this column, and you know that column would be the second row of the n by n multiplicative identities, so I would get 0, 1, and then zeros all the way down. So if I multiply that by the scalar lambda 2, I would get 0, lambda 2, and then zeros underneath. Okay? And then we just keep going on the same way. So it's the same reasoning here. Okay? All the way down to the end until the very last column is all zeros, with the bottom being lambda sub n there. Okay? And you can see that's going to be what? That's going to be a diagonal matrix. Okay? And notice that my statement up here was indeed correct. The diagonal entries of D are actually what? The eigenvalues of A. Okay? Okay, those are going to be the eigenvalues. Again, I could actually scramble in this. This P is not unique. Do you see I could actually scramble the order in which I had written those eigenvectors? Okay? I would still have an allowable P, right? But my D would end up what? I would be permuting my values of my eigenvalues here also in D at the end. Okay, but there it is. Okay, let's look at the other direction. So conversely, suppose that A is diagonalizable with PAP being our diagonal. Okay, for some matrix P, I want to show that P actually does consist of a matrix with columns that are eigenvectors. Okay, so we want to show its columns are eigenvectors of A. Okay, let's just say these are the columns. P is x1 bar, x2 bar, down to x sub n bar. Okay, and let's say these are the diagonals. Okay, they happen to be lambdas, but we're pretending we don't know those are eigenvalues. Okay, all right, let's jump in here. It's really not very hard. P inverse A times P was supposed to be D. Now, if I multiply on the left on both sides by P, you can see that this equation above would reduce to that. This is equivalent to saying AP equals PD. Okay? All right? But P inverse is assumed to be, what, invertible. Okay? So these two are actually equivalent. Okay. Now, what would AP look like? Well, what is P? Here's P up here. If I was to multiply that on the left by the matrix A, that A would multiply on each of these columns, and I would end up getting this then for the product. Those would be the columns of the product here. Okay? Now, remember, AP is supposed to be equal to P times D. Well, P times D, that's pretty easy because I'm just going P times this diagonal matrix. If you multiply these two matrices, those are really easy to multiply together. Okay? You see what you're going to get here. This could be an exercise for you, but you're going to get the first column being what? Lambda 1 times the first column of P, and the second column of the product is going to be lambda 2 times the second column of P, and so forth all the way down to the n. Okay? And now, remember, these are both n by n matrices, and these are corresponding columns, so these could be equated. So this, for example, A times x sub 1 bar should be the same as what? Lambda 1 times x sub 1 bar, okay? And then A x sub 2 bar should be lambda 2 times x sub 2 bar, and so forth, all the way down to the nth vector there at the end. A times x sub n bar is lambda sub n x sub n bar, okay? So what we really have is that what? A times x sub I is lambda I times x sub I bar for I equals 1 to n. In other words, for all of them. Well, wait, this is what we mean by eigenvectors and corresponding eigenvalues. Or I should say eigenvalues and corresponding eigenvectors, right? That's what we mean by eigenvalues, okay, and eigenvectors. Okay, so we proved it, okay? All right, one last comment I want to make here. Because P is invertible, the eigenvectors of A must form a basis of Rn or Cn in the case of a diagonal matrix P. Yeah, because if you come back up here and look at these, remember these are eigenvectors, okay? Now, in order for a matrix to be invertible, you remember the columns or the rows, and the rows, have to be what? Linearly independent, right? Okay? Well, if I've got n of them, and they're linearly independent, then it's got to be a basis, right? Okay? And so it's going to be a basis for Rn. Alrighty? Alrighty? Now let's take a concrete example. I've taken kind of a simple one here. But suppose A is the following matrix. This isn't a diagonal matrix, it's an upper triangular matrix. But reading across 5, negative 1, 1, 0, 1, 3, 0, 0, negative 4. And I claim this can be diagonalized, okay, or has a diagonal form. That's another common notion, or another common way of saying it, okay? Diagonalizable or has a diagonal form, those mean the same thing. Okay, let's go ahead and show that that's actually the case, okay? You remember on an upper triangular matrix, it's easy to find the eigenvalues. They're just what? The values down the main diagonal, right? So the eigenvalues are 5, 1, and negative 4. Okay? Now in my formulation, I actually use this form, which is what I'm more used to. Okay? But I did this. I'm going to solve this. A minus lambda I x bar equals 0 bar, right? I'm looking for the eigenvectors corresponding to these particular eigenvalues up here. Okay? All right. Also remember, any non-scalar multiple of an eigenvector is an eigenvector. right? Okay, let's start with lambda equals 5. So what am I going to do? I'm using this formulation, a minus lambda I. So I'm just subtracting lambda all the way down the main diagonal, and otherwise leaving this alone. And then that's being set to 0. So what you would get is the following. 0, -1, 1, and then 0 on the other side, right? 0, -4, 3, 0 on the other side, 0, 0, -9, 0. Okay? Then I went to row reduced echelon form, and I get this 0, 1, 0, 0, 0, 0, 1, 0, and then 0 is all at the bottom here. And you can see here, this would indicate that what x sub 2, if I was to call that the second component, and x sub 3, those both have to be 0. X sub 1 is free though, okay? So I went ahead and made it, just took an easy value. I just made that equal to 1. But these two, x sub 2 and x sub 3, have to be 0. Okay? Now you could double check that this is actually an eigenvector. I didn't go through that, but it's pretty easy. Okay? And then my next eigenvalue is lambda equals 1. So I went up here and subtracted 1 from each element of the main diagonal, and then I set that to 0 here. Okay? So I got this 4, -1, 1, and then 0, 0, 0, 3, 0, 0, 0, -5, 0. Okay? Row reduced echelon form 4, -1, 0, 0, 0, 0, 1, 0, and then 0's on the bottom telling us nothing. You can see that x sub 3 here this time would have to be 0, so I've got that there. And then there's infinitely many solutions to this up here, of course. Okay? But all we need is one of them here. All the rest are scalar multiples of this, so I went 1, 4. So I've got this eigenvector, 1, 4, 0, with corresponding eigenvalue 1. And you can double check that that's actually the case. I ran out of room here, so I didn't want to do that one. Our last eigenvalue was -4. So let's deal with that one. Lambda equals -4, so I subtract 4 down the main diagonal. 9, -1, 1, 0, 0, 5, 3, and then all zeros on the bottom. I row reduced echelon form. I got 1, 0, 8 45ths, 0, 0, 1 3/5, 0, and then zeros at the bottom. And I chose this for my eigenvector here, x sub 3 bar, -8, -27, 45. Okay? Alrighty. Now, to form my P then, what do? I just take the eigenvectors I chose. Okay? Okay, now there's infinitely many ways to do this, right? I could have scrambled the order on those columns, or I could have used what? Different multiples on these, okay? I could have used 2, 0, 0. I could have used 1/4, 1, 0. You know, here I could have had what? -8 45ths, -27 45ths, and 1, or something like that, right? Any non-zero scalar multiple of the various columns would work. Okay, but I chose one, okay, and I chose that one. And then I used my calculator. I actually came up with the P inverse here. Okay, so I got 1, -1/4, 1/36, 0, 1/4, 3/20, 0, 0, 1/45. Okay, use the frac button on your TI to get it into a fraction here. And then I just double checked, actually put this in my calculator, and I got P inverse A times P, and we get, what did we get here? We got a diagonal matrix D, 5, 1, and -4. The eigenvalues that we knew would appear. Okay, so it worked. Let's take another example real fast here. I've got this 2x2 matrix, 2, -2, 2, 6. It has no diagonal form. In other words, it is not diagonalizable. Okay, I'm going to do it my old-fashioned way, determinant 2 minus lambda, -2. So I'm going A minus lambda I. And then I get 2, 6 minus lambda. The determinant turns out to be, comes down to this. Lambda squared minus 8 lambda plus 16 is 0. And you can see that's going to give you what? A double root, right? -4 occurs as a 0 2 times, okay? So when I come up here, I've just got lambda 1 equals 4. And when I subtract that down the main diagonal here, setting it to 0, I get non-zero scalar multiples of this vector, 1, 1. Okay? And you could actually go ahead and see if that works on the original here. I hope it does. Did I do that right? Okay. 2 to -2. Oh, wait. No, this should be, I'm sorry. This should be what? -1, right? Yeah, let's do this. There's a -1. Okay, that's better now. That should be -1. It still didn't help, though. Do you see I've only got one eigenvector? Well, non-zero scalar multiples of this, but I've got essentially just one eigenvector this time. I can't put these together in a matrix, scalar multiples of each other, and have it, all right, let's do this. Let's say this. I can't have this as my P. Is that invertible? Well, certainly not. The columns are not linearly independent, right? Okay, this isn't going to work. This doesn't have an inverse. The determinant is 0. Okay, sorry, it's not going to work. Alrighty, let's mention a theorem here and a quick corollary, and then we'll be done. Let A be an n by n matrix with distinct eigenvalues here. Okay, these are the distinct eigenvalues. Okay, now you remember that the characteristic polynomial is actually of degree n, right? Degree n. So it's going to have counting multiplicity n zeros if you go to the complex numbers, right? N zeros. They may not be all distinct though, right? All right. So you may have some repeated ones, is what I'm saying. Now suppose that the distinct eigenvalues are lambda 1 through lambda m. Okay, so m is less than or equal to n. Okay, you can't have more distinct zeros than you have zeros, right? Okay, but let's say this. If x sub I is an eigenvector corresponding to the eigenvalue lambda sub I, okay, so for each one of these distinct ones, okay, I've got corresponding eigenvectors, okay, then these are going to be linearly independent, okay, so that's a theorem that you can use. These are going to be linearly independent, all right? So eigenvectors corresponding to distinct eigenvalues are linearly independent. Think of it that way. Let's talk about a quick corollary here. Suppose that A is an n by n matrix with n distinct eigenvalues. That means all the eigenvalues are distinct, right? Because it's an n by n matrix. There's a total of n eigenvalues. This means you wouldn't be repeating any eigenvalues, right? No repeats. Okay? That would mean what then? Then you would have what? N corresponding, this should be an M here, by the way. Oops. There would be what? N eigenvectors corresponding to, because of corresponding to each one of those eigenvalues, there's what? An eigenvector. Since all those eigenvalues are distinct, that means all those n eigenvectors would be linearly independent, but that means they would be what? They would be a basis for Rn, or Cn, depending on the situation you're in, but that would allow what? We said that previously. That means that P would be invertible there, right? Okay, so that means A would be diagonalizable. So that means if you've got n distinct eigenvalues for an n by n matrix, then it's certainly going to be diagonalizable. Okay? Alrighty, I gave you some problems for the homework sets here, and then I think you should be okay. Alrighty, hope you understood that.